very strict. Very strict.
Organizer, please take a seat. Welcome to the second talk this afternoon. It's by Yfke Dulek. She's a PhD student back at home in Amsterdam at QuSoft. And she's going to talk about authenticating quantum states.
Thank you for the introduction and thank you for having me here today. So this last talk, I want to present to you a tool in quantum cryptography, authentication of quantum states. This tool in itself is also an application. Maybe you want to authenticate a quantum state. That can be a goal in itself. But my goal today is to convince you or to inspire you to see this cryptographic primitive also as a tool to build other things. And I'm going to show you sort of some examples or some samplings on how you might go about doing that. So just informally to get an introduction, what are quantum authentication codes? What does it mean to authenticate a quantum state? Well, the goal of a quantum authentication code is to prevent information from being altered while it's being sent or stored somewhere. So in a picture, you might think of this like this. You start with some quantum state, psi. Then there is some kind of encoding procedure. This is a quantum channel, but it depends on a classical key, k. Then it's being, for example, sent over some quantum channel, and there is maybe somebody sitting in the middle that is attacking this. It's doing some arbitrary thing with the state. And whoever is on the other side and is receiving the state does some kind of decoding procedure that depends on the same key. Either he gets out the original quantum state, or he will notice that something has happened to the state and he will output some kind of special reject state. So this reject state sits outside of our space of possible messages. It's really sort of separating. But you can also use this if you want to, like, I described it as a sort of sender-receiver setting, but you can also think of this as maybe you want to store your information somewhere on the cloud and then later retrieve it. So then you would be the one doing both the encoding and the decoding. If you're coming from a more classical crypto perspective, then you might have seen these two things being called a signing algorithm and a checking algorithm. I purposefully don't use these names in the quantum setting, and it will become clear later why I don't do that. Just to mention some things to put some boundaries on the context. This key, K, is a one-time use. So you can use it once to send a message, encode it and decode it, and then if you want to send another message, then you have to send a new key. And one important thing to note is that so if this decoding rejects, then your information is also gone. And this really differentiates an authentication code from an error correcting code. With an error correcting code, we want to increase the probability that we can always retrieve our information back. But we're also up against a slightly simpler attacker or easier attacker, namely usually some probabilistic noise that is presumed to be somewhat small. Here we're up against an arbitrary malicious attacker that will try to do the worst possible thing to our state. So we cannot guarantee that we always get it back, but we hope to guarantee that we either get it back or we notice that something went. Okay, so we just saw authentication of a state. It prevents that state from being altered at all. But there's a related task that we might want to do that might seem not related in the beginning. We already saw a lot of this today. The verification of a computation. Essentially, verifying a computation is preventing the input from being altered except in the very specific way, namely the computation that we want to do that we want to perform. Or if you look at it from the other side, you can see the authentication of a state as verifying the identity. So I give my input state, my encoded input state to some server, and at the end I verify that they actually performed the identity on my state. So if you don't remember anything else from this talk, I want you to remember this kind of connection that even though they seem quite different at first sight, they're actually very similar. And I want to convince you today that we can use these quantum authentication codes, or QACs, as an ingredient for cryptographic verification protocols. So that will be also the outline for today. The first part, which will be a little bit more than one half of the talk, I will give you a more formal definition of quantum authentication. I will give you two examples of different codes to make things a little bit more concrete. And I'll discuss a little bit its relation to encryption and some other definitions. And in the second part, I will touch upon some applications and two specific scenarios. One, which we have seen a lot of today already, client-server, verifier, prover, this kind of setting, with delegated computation. And another setting relates to some recent work on multi-party computation. All right, so let's get started with the formalities of quantum authentication codes. This study was initiated in 2002 already. And the definition consists of two parts. The first part is pretty simple, straightforward, it's correctness. It essentially says that if nothing happens, then the decryption should always accept. So if the attacker doesn't do anything, so we just concatenate the encoding and decoding procedures, then we should have identity and original message is always recovered. That's not really the interesting part. The interesting part is the security. I'm going to show you a big formula. Don't worry, we're going to digest it a bit. So the security definition that was given by Barnum and others in 2002, intuitively what it says is, if the decryption accepts, then we have to have the guarantee that the recovered message is close to the original message. That's kind of the intuition. And now the formalization is this formula below. But let's digest it a bit. So here on the left, ignore the quantifiers for now, but on the left, I wrote the real scenario. So what happens in the actual case? So we start with some input state row, we encode it, then there is some kind of attack map in the middle that we don't know anything about. We decode it, and we look at whatever state comes out. And because the attacker doesn't know the key, so sort of his attack is independent of the key K, and he doesn't have any information of this key K, we take the average over all keys, and we look at that state. And that's what we say is like the actual state. And then we want this state to be close, in some sense, to some ideal state. And this is a sort of paradigm that we use a lot in cryptography, both classical and quantum, where we say, okay, this is what actually happens with our actual algorithms and our keys and the actual attacks, but it should always be captured by some ideal thing where we really limit what the adversary can do. And in this case, the ideal scenario or the ideal outcome state, it's just the only freedom we give the adversary is to choose some real number A, some probability. And with probability A, he lets the original state through, so rho comes out. And with probability 1 minus A, he sabotages and the reject state comes out. So what this ideal functionality captures is saying, okay, the only freedom that we give to our adversary is choosing whether or not to let the state through, essentially. We can never prevent the adversary from sabotaging the wire and like throwing everything out, but then it will always result in a reject. And this approximation sign in the middle, it really just means that these two states should be, or the difference between these two states should be close in trace norm, up to some factor that's negligible in some parameters that live inside this encoding and decoding. Any questions about this definition? It can be a lot to take in if you see it for the first time.
Are you really interested in mixed states, or do you really care only about pure states?
Well, in this case, I want to write it as a mixed state because it's really sort of a probabilistic mixture, and it can be a classical mixture over these two things. Like the adversary can choose to flip a coin and like sort of either do this or do that. But you see here that I also wrote that this is a first attempt. So I think
it's a little odd because the rejection is a pure state, but the ideal thing was a mixed state.
Yeah, the original input can be kind of anything, and it can also be entangled with something. But usually what this decoding protocol would do is like it detects some kind of error, and then it just traces out the original message and replaces it with some fixed state, and that can be a pure state. So this is what usually these things do in practice.
But wouldn't it be satisfactory to output a single bit, 0, 1, and then have the rest of the state be any arbitrary thing?
Yes, you can also do it in this kind of protocol. So to have a separate register where you have a kind of flag that says accept or reject, that's also perfectly fine. But then in the reject case, you have to specify what state is in this reject state, and that's really because we're working with this real ideal scenario then it becomes the question, like in the ideal scenario, if we reject, what should be in this other state? Yeah, so this really captures a lot of the intuition of what we want from authentication. And during the rest of the talk, you can also kind of think of the authentication like this. It will be perfectly fine. Oh,
so you say there is also a rejection state up there in the quantifiers, right? There is an A and there is a rejection state.
Well, the rejection state is just some fixed states. You can just think of this as, for example, 0, like the all 0 string or something, and just some state that's not allowed to be used as a message. We can fix it forever. And these quantifiers just says that for every attack, so anything the adversary can do, we can always kind of simulate it by having the adversary just choose only this parameter A, such that these two things are the same for all input states. So we don't parameterize over this reject state. It's just a fixed thing.
K is always a classical string. So
Yes. Oh, yeah. Thank you. Yeah. So the encoding and decoding procedures are quantum maps, but the key is always classical. But okay. So this is all nice and fine, but somehow it doesn't really capture everything that we can do in the quantum case. So let me show you one example. So suppose that we start with some state. I'm going to write just a pure state now, just to make things a little bit shorter. So we start with some state psi. We encode it. At some point, we will decode it again. The attack in the middle will be the following thing. So the adversary just prepares in his own memory some extra qubit. So he will start in a state 0. Apply a Hadamard, so it's now in the state plus. And then, conditioned on this wire, he will perform some kind of attack on this state. Now, this may be multiple qubits. Let's say that if this was a single qubit, then the encoding, if this was a single qubit, maybe the encoding consisted of m different qubits. Right, the encoding map might blow it up into multiple states. And he will just apply some outrageous attack, like flip everything, that will for sure be detected by our decoding. But he only does it conditioned on this wire here. So then you can ask, okay, so what do we get out at the end? Well, what we get out is, we can quite easily compute what we get out. We get 0 times the original state, because if this is 0, then nothing happens and we always accept. Plus, if this first wire was 1, we will get the reject state here. So here we really have a kind of situation where at the end we have some kind of entanglement or some superposition between acceptance and rejectance. And we don't see this, of course, in the classical world. And it's kind of also not really captured by this definition. I tried to think of an example of some encoding, decoding that would satisfy that definition but didn't do what we want. I couldn't really think of one. But still, I hope you agree with me that kind of not everything that can happen in the world is captured by this definition.
No, I actually don't see that. So why? So if you trace out the 0, then you get something.
Yeah, so if you trace out the 0, then you still get this thing. So this example really satisfies this definition still. So it's not really an example of why this definition is wrong. It's just that if you look at this as the thing that happens in the ideal world, it's not really what happens, right? Because this seems to suggest that we always throw out all the entangled wires, whereas we actually keep some of the entanglement, and maybe this adversary will measure his wire afterwards, and I feel that it's not really captured by this definition. Yes, exactly. So if we just look at this state here that comes out, then we will have, with probability 1/2, we will have the original state, and with probability 1/2, we will have the reject. So we have a mixture of those two. Yeah. So it still satisfies the definition, but somehow what happens here is not really captured there. So I'm just going to...
Try to think of an attack, a concrete attack that you would like to prevent, but this definition doesn't. So at the end of the decoding process, are you saying that I have this state, which could either be the original state or reject, and I don't know what it is?
Mm-hmm.
depending on what happens in the world, the adversary can make it one of the two, and that classically, that doesn't happen.
Yeah, although he cannot really make it one of the two, but at least he cannot decide what will happen, but he can fix what will happen, kind of.
So it's a problem with composition or something, if this was used many times in parallel? Maybe?
Yes, maybe something like this. I couldn't think of a simple example. Maybe we can think about it offline. But anyway, just to continue, so a sort of more general definition that will anyway capture all of these things was given 1 decade later by Dupuy, Nielsen, Savai, where the core of the definition is really the same. So if you just want to think about this one, that's fine. But here we add this side information wire, so whatever information the adversary still has. So the only difference is now that our input state row is both on a message register and a side information register, so it's a joint state. Our encoding and decoding still really only happens on the message register, so just identity on the side information, but the attack, so whatever happens here in the middle, can happen on both. And then what we say is, instead of requiring that there is some kind of probability A that chooses one or the other, there should be 2 quantum maps, the phi accept map and the phi reject map, that act only on the side information register, so that our real case here on the top is approximately equal to the ideal case, where in the ideal case, either nothing happens to the message and the accept map is applied to the side information, or the message is rejected and then the reject map is applied to the side information. If we look again at this picture here, then the accept map would just be identity, right? This 0 would be the side information, and this psi would be the message register. And the reject map is just a bit flip. And our starting state row would be the tensor product of the 0 and the psi. Anyway, this situation is still captured by this. This is just really a more general version of this one, which captures the quantum effects a little bit more nicely.
Minor question. Should that circle be a tensor product on the bottom right?
Yes, you're right. Sorry. Yeah, this should be a tensor product. Thank you for pointing that out. Okay, now we've seen all these long formulas. Let's just go to some examples to make it a little bit more lighthearted. The first example is a Clifford code. Maybe a quick show of hands. Who would like to see a definition or a recap of this Clifford code? Okay, I see some hands. That's great. So you may be familiar with the poly group. The n-qubit poly group, we've seen it also already in some previous talks. It's really just the tensor product of I'm writing xz, but you can also think of y here. Right, so the n-qubit poly group is just a tensor product of n polys and can be any combination of identity, bit flip, phase flip, or both. And the Clifford group on n qubits is defined in terms of this poly group. So it's really the set of unitaries on n qubits such that for all polys in the n-qubit poly group, the conjugation of that poly with this U is still in the poly group. So and then I'm going to make a few minor changes because I don't want to worry about phase in this case. So it can be either in the poly group or in minus that thing. And I'm going to take the quotient over just all the numbers with norm 1. So the Clifford group, it's kind of all the things that map polys to other polys by conjugating them. And one really cool property to mention about this Clifford group is that if we take any poly element that's not identity, and we conjugate it with a random Clifford element, then we get a random non-identity poly. So this it has kind of a sort of randomizing effect on the poly group as well, and that will be important later on. I'll reiterate it at that point. So anyway, the Clifford group, it's just a group of unitaries. It doesn't do all quantum computation. It doesn't even do classical computation, but it's still a pretty big group of operations. And in Clifford code, our key is going to be a random element from the Clifford group on n+1 elements. N is just some parameter here. Security will depend on n. And to encode a state psi, what we will do is we will append a number of zeros to the state. We call these states usually traps. And then we just apply this random Clifford to it. And that's it. That's all we do. So this is like our authentication of the state psi. And then to decode, we just do the inverse. So we apply the transpose of C, our key, and we measure whether all these trap positions in the computational basis, and if they're still all zero, we'll say it's fine. And if they're not all zero anymore, then we will say, oh, something went wrong, and we reject.
Just to make sure I understand, the key is enormous, right? 2 to the 2n.
Is it? I think it's something like n squared or some order of n squared, right? It's big, but not enormous, I think. And one can show that the Clifford code is a secure quantum authentication code. The proof is actually really short. I think I have time to do it, so give it a try. So I will just show that the Clifford code is secure if the attack is a poly attack. And we've just seen in Urmila's talk that we can generalize this to general unitary attacks using this poly twirl. You don't really have to worry about that. I'm just going to do a sort of special case because that already kind of captures the main ideas of the security. So let's say that we have some attack map that is some poly. So I'm just writing this like it's the map that applies the poly to its input state. And to keep things interesting, we're going to assume that this poly is not the identity, because otherwise it's going to be quite a bit boring. So we want to look at the real state, which was the expectation over the key. In this case, the key is a Clifford of the decoding our attack map and encoding. So we're reading it from right to left. Applied to some input state psi. I'm again going to use a pure state here just because it's shorter for notation. And we hope that this is equal to something in the ideal world. So let me first write out what this state looks like right before we perform the measurement of the decoding. So the decoding ended with measuring the trap, so I'm just going to write the pre-measurement state. So that looked like, okay, so first we encode the state, so that's applying our Clifford to psi tensor some row of zeros. Then the attack happens. Well, we just assumed that this was a poly. And then we decode it by first applying inverse of the Clifford, and then after this we're going to measure. But remember that we took a random Clifford. And I just mentioned earlier when I was defining the Clifford group that if we take any poly that's not the identity and we conjugate it with a random Clifford, then what we get out is a random poly. So this state is actually equal to taking a random poly, let me call it P prime just to distinguish, and apply this P prime to psi tensor the zero state. Well, if we now measure this state that we have here, if we measure this, what is the probability that we're going to get the all zeros outcome here if we measure it in the computation basis?
Very low.
Very low. Any takers? Hint, it's on the board. Okay, so this is the probability that if you apply a random non-identity poly here, the probability that you'll get the all zero measurement here is going to be 2 to the minus n, because essentially you have to have identity on all of these positions, and then maybe non-identity here. So that means, so this is our sort of pre-measurement state and our post-measurement state. So what's written up here, well, with overwhelming probability, it's going to be equal to the reject state. Because we're going to measure something non-zero, and then we're going to reject. So if we took our original definition with this just this parameter a, then a would be equal to almost equal to 0. So that's the security of the Clifford code. It's a fairly simple procedure in how it works, but it's also a fairly powerful code. That makes it very nice. The second example of a code is the trap code. This one was just a little bit later developed by Broadbent and others in the context of quantum one-time programs. The definition sounds a little bit scarier, but I promise nothing really weird is happening here. So instead of taking a random Clifford as the key, we will take two elements, namely a random poly, so that's a sort of simpler thing, and a random permutation. And both the poly and the permutation are going to work on 3n qubits. But the n is again just some parameter. And then the encoding is this whole thing. So I always like to draw this in a picture. This is an error-correcting code that takes a single qubit to n qubits and has some distance, so the minimum number of alterations that you have to make of d. But let's draw this in a picture, what's going on here. So the encoding works as follows. You start with your single state psi. You append a number of pluses. This is plus to the n, and a number of zeros, which are sufficient for this 0 to the n, and some extra ancillas for your error-correcting code. So the first thing you do is you apply an error-correcting code, which essentially spreads out your data from one qubit to multiple qubits. That already protects it a little bit, right? That it's not in a single location anymore, but in multiple locations. Next thing you do is you apply this random permutation, so everything is jumbled up. And finally, you apply a random poly, which is a quantum one-time pad, so that really hides which qubit is which. So if you now give me this state, and I don't know what pi or p is, then I have no clue whether this is a data qubit, a trap qubit, or a different type of trap. So we have our red qubits here, which are sort of spread out the data that needs to be protected. We have the zero traps, which will detect whether an attack has happened in the computational basis, and we have plus traps, which will detect whether an attack has happened in the Hadamard basis. And the decoding is really similar to that in the Clifford code. So we essentially just undo everything and measure whether the zeros are still zeros, whether the pluses are still pluses, and whether the error-correcting code also didn't detect any errors. We can also show that the trap code is a secure quantum authentication code. The proof will be quite similar, but I'm not going to do it now.
This is a lot like what's done in quantum key distribution, where ECC is a CSS code, right?
Yes, yeah. Or you also have these kind of zeros and pluses to protect the,
And the two different bases.
I think probably the underlying ideas are the same. So the trap code is also secure. Its security depends on the distance of the error-correcting code that we use, but we can use, for example, an error-correcting code with distance square root of n, and then we would still get something negligible here.
Can you explain what the error-correcting code is for?
So the error-correcting code is really, let me see if I can pull up the picture quickly again here, to make sure that if you want to attack, like if you want to alter psi, you need to alter a sufficient number of locations in this random permutation. So it's not like if you wouldn't use this error-correcting code, then you would have a single qubit in here that would be red, so representing the data. And then you could potentially alter the state by guessing its location. So you would have inverse polynomial probability of succeeding in your attack. And this error-correcting code just makes sure that that's harder because you have to attack more locations.
So it's to get exponential.
Yes, exactly. Okay, now I'll show you two codes. They look pretty similar, but which one is better? Well, there's no real answer to this. It just kind of really depends. So the Clifford code, it has a really clean and simple definition, and the analysis goes through pretty nicely and has pretty strong security. And on the other hand, the trap code has some more structure to it. So we will see this in the second part of my talk, that this structure allows you to perform computations on the encrypted data more easily in some sense. And also the encoding and decoding procedures, these maps, they require in some sense less quantum. So the encoder doesn't have to apply a full Clifford operation, but they just have to swap some wires and apply polys, which arguably would be simpler to do, depending on...
There's also the code, right?
Sorry?
The code might be-
Yeah, the code might be, but I think there's some codes that do have the right properties that are just some C notes, I think. CSS codes, I think they're like, you start with some zeros and pluses and you use some C notes, so that could be relative, but yeah, I agree. It really depends on what you think is easy things.
And the Clifford circuit, how do you get the circuit from the Clifford?
It's possible to just, I think it's just possible to efficiently sample a Clifford and compute what would be the circuit that belongs to it. But there's more than these two codes, of course, that I showed you. There's the polynomial code, which is already, well, maybe one of the oldest. There is a more recent one, which really nicely captures the idea that we have to authenticate two bases. So it uses a classical authentication on the computational basis, then it performs a Fourier transform, and then it does the same thing again, so on the other basis. And there is some variant of the trap code as well. So it really depends on sort of what you're doing, which code is the most natural to use. There's a whole landscape of different definitions out there. So I've shown you this like original attempt at the definition and a slightly sort of fix of that definition that was given by Dulek and others. But there's more definitions. For example, there's a stronger definition that is concerned with key recycling. So that asks the question, like, if everything is fine and the decoder accepts, that can we then reuse the key for another round? That's a strictly stronger definition, of course. And we know that the Clifford code has this property. The trap code does not. I don't have time to show an example. Unfortunately, you can just talk to me after. Another stronger variant that is sort of on another axis than this key recycling is the idea of ciphertext authentication. So what we've seen so far is only plain text authentication. We want to protect this underlying state psi, but you might also say, I want to guarantee that nothing happened even to my ciphertext. And this is somehow, I think it's closer to the classical definitions of authentication that we have. And in this work, it was used to define like some stronger notion of encryption and some quantivariant of CCA2. And we know that both the Clifford code and the trap code provide this property. And one last thing that I want to mention in this first part of the talk, which to me was very surprising at first, because this is really not true in the classical world, is that if you have an authentication code, it is necessarily also an encryption code. I will not give you a formal proof, but I can give you some intuition. So in quantum mechanics, we have this idea that if you measure in one basis, so if you get information in one basis by measuring, then you necessarily disturb the other basis. So if you turn this around, like contrapose this statement, then you see if you want to make sure that the other basis cannot be disturbed, if you want to authenticate the other basis, then you must make sure that in this first basis, no information can be given away. So in other words, if we want to authenticate one basis, then we necessarily have to encrypt the other basis. If we want to authenticate both bases, that also means we need to authenticate both bases. This is really a phenomenon that's uniquely quantum. This is also the reason why I've been using like encoding, decoding, or sometimes encrypting, decrypting, rather than signing and checking.
Could the statement be made to go both ways? So any quantum authentication scheme gives a QKD scheme. Any QKD scheme gives a quantum authentication scheme?
So I don't think any authentication scheme gives a QKD scheme. It's not a key distribution scheme, but it's like it also hides the information of the underlying state. So it's also an encryption scheme.
Oh, but it decodes it and gives back the original state, so that distributes keys. Since all you have to do is distribute an EPR pair.
Yeah, I guess you could use it to construct a QKD scheme. Whether it then goes the other way around, I really don't know. I don't see immediately why that would be true, but maybe.
Because if you detect the eavesdropper, then it's your reject state, and it's kind of like,
maybe.
It's kind of like in digital signature schemes, you can show that a one-way function always gives a DSS and vice versa.
Mm-hmm. Yeah, there might be something there. I wouldn't be able to like give you a definitive answer as well. Thanks for listening. So just to end this like first part of the talk with some open problems, because well, maybe you would like to also work a little bit on this idea of quantum authentication. I have a small list of open problems. It's by no means exhaustive, and there are some references that I put after every point. They're not necessarily the paper that posed this question or the paper that attempts to answer this question. It's just the point where I would suggest you start reading up if you are interested in tackling this problem. So I briefly mentioned this key recycling, and in the GYZ paper, they give a definition of key recycling, which states that if the codes accept, then the key should be used again, be used again. But you can also ask the question, like, if the decoding rejects, how much of the key is actually compromised? Can we reuse it entirely? Can we reuse part of it, maybe? This is really nothing is known about this. You can generalize this question also a little bit, like, can we design new codes that maybe require or allow us to reuse the key many times? And then you almost get into the realm of digital signatures. Another question is how to deal with noise. So the codes that I showed you today are really strict, right? If we detect just a single error on our traps, we immediately reject and throw out everything that we have. And maybe that's a little bit too strict. And of course, you can salvage this by throwing an error-correcting code on top of everything, but that also feels like you're doing double work. So maybe can we kind of combine the two and give some threshold above which we reject, but below with which we say, oh, it's probably just regular noise. And one that I personally find very interesting is sort of what are the minimal capabilities that we require from our encoder or decoder? Can we maybe, through some interactive means, have a classical client outsource the encoding? This really relates a lot to what Urmila talked about earlier this afternoon, where we ask a prover to sort of prove that they have a certain quantum state. I wonder whether it would be possible to make a prover prepare an authentication without them knowing the key. We have some ideas on this already, but it doesn't quite work yet. But I think this is a really cool question.
So the client actually gets the quantum state as input, right? So
Mm-hmm.
can they be classical?
Yeah, so you can imagine a scenario where maybe the client wants to create an encoding of a specific known state, like the zero state or some. I can maybe better comment on this at some point after the second part, because then we can see a application of this last question, essentially. There's probably many more nice questions, but these are just a few that I think are interesting. So, any questions about this first two-thirds? Authentication codes, the Clifford code, the trap code, its relation to encryption. If not, then let's move on to some applications. We already saw a lot of verifiable computation here. Some of the things that we already saw earlier today are sort of further in terms of timeline than what I'm going to present to you here. So some of the things that they achieve might be actually better than what I will present here. But still, I hope to convince you that this is a really sort of nice application of authentication codes. The first scenario is just a client and server, or you can think about it as a verifier and prover. The client has some input, some quantum input, and wants to do some quantum computation on it. And the prover is going to help the client in doing this, but they are not they're not trustworthy. So the client would like to verify that the server actually did what they were supposed to do. So the picture is really similar to what we had in the beginning. We start with some input say psi, which is encoded, then given to our untrustworthy prover that's hopefully going to perform some computation. Then we decode the state again, and either we get the result of our computation here, so this C is now not a Clifford, but just some quantum circuit, or we're going to reject. So this is done by a client, server, and then again client. Crucially, of course, the server doesn't know the key, otherwise these things would become very simple. And if you look very closely, you might see that the client doesn't necessarily decode with the same key. So as part of the computation, the client may update their key. So the update will depend on the original key and whatever the computation was supposed to be. But this will all be sort of classical computation usually. And I think the kind of most standard or basic protocol was proposed in 2013 as part of some bigger protocol for one-time programs. And this protocol is using the trap code and will evaluate this circuit C gate by gate. Some gates will be simple and some gates will require some extra ingredients called magic states. And the idea for the simpler gates is to use transversal gate application. So you may know from, for example, error correcting codes that if you want to apply a gate, for example, a bit flip gate on the logical underlying data, what you can do is just apply a bit flip on every single physical qubit, and that will result in applying a logical bit flip. And that idea is what we're going to use here as well. So we're thinking in this trap codes scenario. So we have our data, which is kind of spread out using error correcting code. We have our 0 traps for the bit flips and our plus traps for the phase flips, and they're all nicely permuted and with a one-time pad on top. And what we would like to do is the following, right? We would like to transversely apply, for example, a bit flip on our data. So we would like to have the server apply an X exactly on all these positions. But the server doesn't know the permutation, so he cannot do this. So what we can do is the following. We can just apply an X everywhere. The server can certainly do this. Just apply an X on every wire. And the first thing we can observe here that this is actually the same thing as if he would have applied an X only on the data and the 0 trap positions, because a bit flip operation on a plus trap doesn't do anything. Okay, so that's just enough identity there. Now I'm going to take these two things a little bit apart. This is the operation that we actually wanted the server to do, bit flips on all the data qubits, but he did a few too many. He also put bit flips on all the 0 traps. But the client can fix this classically on her side. So she has, as part of the key, a one-time pad, which is a poly, which consists of X's and Z's. So she can just update her key to kind of undo these unwanted X's. So she will add like extra X inverses to her key as well. And then with the help of the client, the client essentially did most of the work here because they're going to, in the end, decode again with these X's, but okay. With the help of the client, the server, without knowing the key, has applied X's exactly to the positions dictated by the key. And if you're very sharp, you may notice, then the client might as well, the server might as well have just done nothing, and the client could have just updated the key on the data positions. That's perfectly true. That's also actually what we would usually say to do, but I think this is sort of a nice way to expose the general idea without getting into too many nitty-gritty details with the simple X gate. So that's the underlying idea of many gates, and this idea of transversal computation works for, the poly gates, so the X and the Z, also works for the CNOT, and surprisingly, it even works for computational basis measurement. So the server, if they want to do a logical computational basis measurement, can just measure all the qubits, give the list of classical measurement results to the client, and the client, from this list of results, can compute the underlying measurement result.
This is assuming you're using a stabilizer code, right?
Yes, so it does put some requirements on the error correcting code that you're using, that's correct. Yeah. But there's plenty of codes out there that will do the trick for you. Okay, so this is pretty nice, but not really all of the gates that we want to be able to do. So the other gates, they need a little bit of a different trick. And the trick is using magic states. And outside of the scope of authentication and verification, what a magic state does, or a magic state computation does, is the following. Suppose that we have our input state, psi, and we want to apply the following gate on it. So this is just the phase gate, which square root of c. We want to apply this gate to psi, but we don't actually have the components in our circuits to apply this gate. Well, if we have access to this state, which we'll call the magic state, so this is the phase gate applied to plus, and we just perform this circuit here, which you can work out for yourself on a piece of paper if you're interested. But suppose that we could do this entire circuit here. So it consists of a C0, some measurement, and some classically controlled polys. Then what comes out at the bottom is exactly our phase gate applied to original input state. So this is known as magic gate computation. It pops up in different areas in quantum computing. But the crucial thing for us here is that this circuit here in the middle only consists of operations that we already kind of know how to do. So if we have an encoding of our input state psi, and we somehow manage to get hold of an encoding of this magic state here, then we could do this entire circuit under our trap code, so on our authenticated data, and we would get out an encoding of the resulting state. Of course, this does require us to somehow get hold of these like magic states, and this is where your question from earlier comes in. So what if we can have a classical client that can somehow force a prover or a server to prepare an authentication of this known state? So then the client doesn't have to have this state in our hands at the beginning. It's just a sort of publicly known description. But can we somehow find a way to force the prover to prepare such a state? That's kind of why I think this question would be most interesting. But you see, so this protocol, it computes unauthenticated data gate by gate. Some gates require authenticated magic states, in particular these three gates, so this phase gate that we just saw, the Hadamard, and also the non-Clifford T gate. And this non-Clifford T gate even requires some interaction between the client and the server. So this, like, if you look at the actual resources that you're using, is not a very good protocol, right? The client is still doing all of the work. They have to update the key, they have to provide all these authenticated magic states for most of the gates that we're doing, and even have to interact. We can get rid of this interaction between the client and the server, and then we somehow get to a sort of verifiable homomorphic encryption, but it still requires a lot from the client.
But all this quantum computation that the client does, can it be preprocessed?
Yes, so that's, yeah, very good question. So that's actually what we do in our verifiable homomorphic encryption paper. Essentially, the client beforehand prepares a whole bunch of these like authenticated magic states, and this interaction is taken out by some other gadget so that the client can do some of that processing also, or the server can, with a classical homomorphic encryption scheme, do some of this processing, and the client can just decode the result at the end. Yeah, so you get, it's independent of the actual computation, but it's still, of course, a lot of work. This is the T-gate magic state protocol, and the reason that it requires some interaction is that this correction here is not a nice quality. Okay, any questions about this sort of general idea?
So at some point you said that the attacker shouldn't know which bits are data and which are error correction. If now the client has to supply some extra information, doesn't that give information to the attacker?
Yeah, except that yeah.
I abuse this information instead of doing some computation with it. I measure it. Now I know where the data is and where the error correction is.
Yeah, so the information that's supplied to the server by the client, it depends on the key because it's also, again, sort of encodings. But what we should take care of, for example, in the trap code is to use fresh one-time pad keys so that information is not really reviewed. And the key updates that the client does, those are really kept private to the client, so the server never brings it. Final part of this talk, I want to give you another application that's part of some recent work, multi-party quantum computation. I could talk for an entire hour about this, so I will just give you a few sort of sprinklings of what's going on. I'm not going to try to give you a full protocol. But in multi-party computation, we have a situation where we have, well, multiple parties, in this case I just drew two, that each have their own inputs. So it's not this asymmetric client-server setting anymore, but it's really everybody has inputs, and everybody could in principle encode their inputs to maybe sort of do some computation together, and they want to check that the other players are behaving as they should. So we maybe want to use some of these like verification properties of our authentication scheme for this. But now a question arises, because what happens if they do some computation together with these encodings where the first player doesn't know the second key, and the second player doesn't know the first key, and how do they even update keys? Who can check whatever comes out and whatnot? So this really gives rise to a whole new challenge. And there's two proposed solutions for this. Each have their pros and cons. The first solution is just to kind of stack authentications. Or in the original paper, this was called swaddling, so sort of wrapping the state into many layers of authentication. And in this solution, what the players do is, well, everybody authenticates their own state, but then they give it to all the other players, and they just kind of put layers of authentications on top. Well, with just 2 players, it looks still kind of feasible. If you have many players, this is going to look horrible. And as you can see, of course, these orders of authentications are also not the same thing. So the nice thing about this solution is that it really has a kind of plug-and-play security. So we have all our security properties of our authentication scheme, so we can kind of just use them here directly, because we're just using them as black boxes on top of each other. But things become a little bit harder. So look, for example, at this one on the left. If player 2, that's holding like the key K2, wants to check this authentication, everything is fine. We can just do this using their decoding. But if player 1 during the computation wants to check whether everything is still fine with their input, like there's this other authentication on top, so they have to do all kinds of classical communication there and make sure that no information about their keys is revealed and everything. So there's some extra work to be done there. And of course, the thing that I already mentioned, if you have more players, the ciphertexts become longer and longer and longer. And there's also some infeasibility if you wanted to T-gate, but I won't get too much into that. But the principal idea works, that we just have everybody do their own encoding, have their own traps, and responsible for their own encoding on everybody's state. Another solution that was proposed a little bit more recently is to do a kind of public authentication test. And the idea here is that, well, there's just one encoding on each state. Usually the other player will also have some input, but let's just focus on the input of the left player here. So there's just one encoding on top of the state, so that's nice and simple again. You can think of this, for example, with the Clifford code. So the Clifford code is 10 some zeros and apply a random Clifford. But the players, they kind of secret share the key to this encoding. So maybe this random Clifford C is actually a product of two other random Cliffords, and player 1 knows the first one, player 2 knows the other one. And you can show, because of the group structure of the Clifford group, that if you know C1, then you don't know anything about C, because you need the C2 as well to get this information. And the really cool thing about this public authentication test, or the thing we want to achieve with this public authentication test, is that we can have one player doing kind of all the hard work, so all the quantum work, all the testing, and all the other players, just with classical communication with that single player, can verify that the player actually did this check correctly. So this really comes a lot into the idea of the sort of verifier prover stuff again. And how it works, well, I'll very briefly show you. The decoding player, so suppose that this player is going to decode and sort of, or not even really decode, but just kind of show that everything is still fine. So maybe it's halfway through the computation, they want to show everything is still fine. What they do is they append another bunch of zeros. So we have these psi tensor 0 with the Clifford on top, and then he just outside here puts another n zeros. And then together with some classical communication, the players settle on this Clifford here. What this Clifford does is, well, first it undoes the encoding on the first, on the actual interesting state. And then it applies a random linear function g. It applies this random g, which is a linear transformation of both these traps that were already inside the encoding and these extra zeros that the decoding player just appended. And the really nice property about this function g is that if everything is a 0, then it does nothing, then it stays a 0. But as soon as this combination of two n strings is not 0, then it will map it to a random bit stream, non-zero bit stream. Right, so even if just one trap is off, then after that all the traps will be kind of broken. Then they apply a new fresh random key again on the actual state, and some random bit flips on this extra register that was appended by the decoding player, just to kind of hide the information there. And then they ask the decoding player to measure this last bit here, or this last n qubits here, and report the value R. And I'm brushing over a lot of details here, so what I'm presenting here is actually not fully secure, because you have to do a lot of work to make sure that if the decoding player learns this Clifford, that they don't learn any information about G or C or C prime. And in the version that I present here, there's actually some information revealed, so you have to do some extra work. But the idea is that all of this work can be done by the decoding player, except for deciding this Clifford, which is some classical communication involved. And then the decoding player, if he acts honestly, he can just measure this last n qubits and reveal R. And if he did anything dishonestly, then this G is going to make sure that everything is mumbled up, and he cannot do anything better than guess R, essentially. Like he can never recover R. So the other players, then they can like reveal some information so that everybody knows what R is supposed to be, and they can really check that this player did what he was supposed to.
How do the players share the key in the first place? Like this is like, say, an n-parted state, and each of them does a C1 on their portion of the qubits. How does it?
Yeah, so a lot of the underlying machinery in our multi-party computation protocol is any classical multi-party computation protocol. So we require, as a sort of ingredient to our scheme, we require a classical multi-party computation protocol, and that really takes care of a lot of the of this type of work. Like, how do they share keys? How do they even like sample a random R together without anybody cheating on that? But there is also some sending states around involved, especially in the encoding phase. Unfortunately, don't have time to give you any more. So just to kind of summarize the idea, so all the players' inputs are encoded. We saw two options for this multi-party computation. Either we can stack the encodings, which gives us nice, simple security, but big ciphertext, or we can do a kind of shared encoding with the public authentication test that I just showed you. And then we can do computations on this with a kind of gate-by-gate computation that's very similar to the ideas that I showed you in the first scenario, the second part, so this client-server setting. And underlyingly, well, corresponding to Andreas' question, underlyingly there's always classical control going on. So there's always this classical leash that we implement by using some classical multi-party computation protocol. So this is also in our scheme where the computational assumptions come in. So some open problems, just to kind of end this second part. I would really like to see some more applications of this public authentication test, because I think as a sort of even outside of the multi-party computation protocol, the idea that we can like force someone to show that everything is still fine without fully decoding the state is really powerful. I'm also interested to see some applications of multi-party computation or quantum multi-party computation. So classically, we already know that it has several applications, and which of these hold true in the quantum world, and how do they compare to maybe some solutions that we already have to zero knowledge, for example? Can we do better with them or not? I don't think there's been a lot of work on this, so that would be interesting to explore. Well, one of my favorite problems, because I've been working on it, I think, already since the beginning of my PhD, is the obfuscation of quantum circuits. The reason that I think this is related to all of this sort of verification problems is that to obfuscate a quantum circuit means to give a user access to some functionality that they can only, like they can use the function, like put inputs in it and get outputs out, but not really learn anything about the function itself. And the reason that I think it's related to verification is that essentially you need to verify that the user used this box in the correct way and only then give them the answer to their computation. And if they did try to do anything else with this box, like trying to find out information about the function that's inside, then they shouldn't get anything. So I think sort of the techniques that we're using in verification, and maybe even some protocols that we already have lying around, could be very useful for this. And this one is maybe more if there's still any lattice people around or some post-quantum crypto people around. In our multi-party computation paper, we use as a primitive, like I mentioned already, a classical multi-party computation scheme. But as far as we could tell, there was not really an established post-quantum secure classical multi-party computation scheme around that had sort of all the properties that we needed from it. And if somebody can make that happen, that would be great. But I don't think there were any fundamental issues with that. I don't know if you recall better, but it seems to be quite straightforward, but we just have to, somebody has to sit down and make sure that everything fits together nicely. So just to end very quickly, some takeaways from this talk. So we saw quantum authentication codes. They guarantee that the quantum state can remain unaltered, unless, of course, we reject, then it's gone. We saw the Clifford code and the trap code as two examples of such codes, but there are many more examples. And these authentication codes can be used as a tool for a client-server setting, like verifying that the server did the right computation. They can be used as a tool for multi-party computation, verifying that the other players did the right computation. But there are some difficulties with that. We need a way to combine the encodings from different players. And I strongly believe that there may be many more applications, but that's also maybe together we're going to find out. Thank you.
I want to try an assertion on you and see what you think, given your deep experience in this area. I want to assert that for every fault-tolerant quantum computation protocol, there probably exists a corresponding quantum authentication protocol and computation protocol of the nature you've described, and vice versa.
And vice versa, okay. Well, I certainly agree with you that there seem to be a lot of techniques that kind of transfer over. And it was not one of the open problems that I listed, but I thought about including it. It seems that in this authentication field, there's lots of like specific codes, and we kind of keep reinventing the wheel. So we have the Clifford code, and then we figure out, okay, how do we do computations on the Clifford code? And then we have the trap code, and we have to figure out how to do computations on the trap code. So it would be really nice to sort of have a unifying framework maybe, or sort of more abstract representations of these types of codes and see sort of what patterns do they follow and how can we do computations on that. And there might be a link with this fault-tolerant computations as well there.
Well, there are recently so many new fault-tolerant computation techniques using peaceable fault tolerance, using meshing lattice codes with triangle surgery, and each one of those differs from the measurement-based quantum computation and the stabilizer codes that are now being traditionally used here. For example, they use multiple codes. They use the Reed-Muller code with a transversal pi/8 and so forth. And I haven't seen those migrate into your field.
Yeah, I have to admit that I'm not super familiar with the sort of most recent development there, so maybe that's a missed opportunity and I should read up on that. Because, I agree, there might be some kind of connection that would be interesting to explore. Thank you.
More questions? One of your questions is that you can solve quantum obfuscation without solving classical obfuscation, or whatever you mean. It's a complicated question, but so we know classically that the sort of strongest definition of black box obfuscation is not possible, right? Sure.
But it's not necessarily the case that if we use quantum techniques that black box obfuscation of classical circuits might still be possible.
And you're willing to make any computational assumption as long as it's not false, is that right?
Yes, at this point, yes.
Yeah, one last one.
I was curious if you have anything to say about the complexity, the communication complexity of these new distributed schemes.
So for our multi-party computation protocol, there's quantum communication and classical communication. We didn't analyze the classical communication so closely because we figured the quantum communication would be the bottleneck. And there, if I recall correctly, the number of rounds of computation is in the order of the number of players times the number of non-Clifford gates, is that correct? The number of T gates, something like this?
Okay, it depends how to do, like you have to do if you do synods or not, so there are variants and then you can count it differently.
But roughly the order of magnitude will be, so for every like a round of Clifford T, you would need to do one round of communication and pass the state around through all the players.
So it's pretty expensive.
Yes, but room for improvement. Feel free.
All right. The invitation to work.